everyone, this is Lakshmi. Welcome to my channel Lakshmi Lucky. So today we'll discuss about Rolle's theorem. It's very important theorem in third unit ma. Yes, the statement has given here, if a function f defined on closed interval a comma b and this function f is continuous on the closed interval a comma b has given and differentiable on open interval a comma b, and third condition is f of a is equal to f of b. So then there exists at least one real number should be exist in this interval ma, that is c belongs to open interval a comma b, so that f dash of c is equal to 0. So anyway, we'll prove one by one this condition. We have two possibilities are there, case 1 and case 2 will do. So in the first given here, since f is nothing but what has given, it is continuous. Continuous means what ma? The function f is a mapping from s tends to r, is a function we can say at the corresponding element ma. Epsilon is greater than 0, there exists a delta is greater than 0, says that mod of f of x minus f of a is less than epsilon whenever mod x minus a is less than delta. Yes, no? That means ma, the function limit of the function x tends to a, f of x is nothing but should be f of a, as epsilon is nothing but arbitrary. So the function f is nothing but continuous means ma, it should be satisfies this condition. So here the condition, the function is nothing but continuous we are taking on the interval, closed interval a comma b. And it is continuous means it should be exist infimum as well as supremum. That means ma, it is nothing but bounded. It should be attains its bounds on closed interval a comma b. Attains means satisfy exist two values ma, that is infimum and supremum, the least upper bound as well as greatest lower bound of the function in the closed interval a comma b. Okay, and it should be exist at least one real number we are saying, no. So we have two possibilities are there ma. I am taking c comma d, two real numbers in between closed interval a comma b, and such that f of c is equal to capital M and f of d is equal to small m we are taking, because m and small m and capital M, these two are infimum and supremum. Okay, that's what I am taking. F of c is equal to capital M, f of d equal to small m we are taking. And here yeah, we have two possibilities. I am saying no, either capital M is equal to small m, that means maximum least upper bound is equal to greatest lower bound, or both are not equal. Okay, we'll check those two conditions. In case 1 I am taking m is equal to small m. Okay, both limits are nothing but equal to each other I am taking. So here f of x is nothing but, the function is nothing but, I am taking equal is nothing but what ma, the function should be equal to obviously constant values. So small m equal to capital M throughout on the closed interval a comma b we can take right now. So that means obviously it should be satisfies continuous condition on closed interval a comma b. So its derivation f of x equal to small m, that should be equal to capital M. Whatever it may be, derivation of that function is nothing but what should we get? It should be equal to 0 right now. So f dash of x should be equal to 0 whenever here x is nothing but always between closed interval a comma b. Okay, and in particular case instead of x we should take c, because here real numbers we are taking c comma d right now. So that's what I am taking, one of the real number c. So f dash of c is equal to 0 when x nothing but lies between open interval a comma b. Okay, and hence we can say this theorem is nothing but true for any real value, that is c belongs to open interval a comma b. Okay, second case we'll see. Yes, we'll see case 2 ma. If in the case 1 we proved ma for m equal to small m right now. Now we'll take both are not equal to each other. Okay, and since we know that here two constant functions are equal, f of a is equal to f of b right now. At least one of the number m and capital M and small m will be the different from the equal values of f of a and f of b we can take, ma. That means suppose you should take capital M is nothing but f of c we are taking. It is nothing but different from f of a and f of b only. That means, ma, now we'll take capital M is equal to f of c. It is different from f of a and f of b we are taking, no. In the first condition, f of c not equal to f of a I am taking. That means what? F of c not equal to f of a means these two elements are also not equal to each other. Okay. And second, capital M is equal to f of c, but it is different from f of b from this condition, right now. So here also these two elements are also not equal to each other. So here c not equal to a is there, c not equal to b. Both are distinct, right now. So here c is nothing but common in between a and b. So that's what my here c is nothing but element in open interval a comma b. So since actually we have the function f is nothing but differentiable on close the open interval a comma b. Okay, that means c belongs to open interval a comma b. So therefore we can say here f is differentiable at the particular point c. Okay, and here it is differentiable at the point c we are taking. By the definition of differentiable, what is that? Left hand derivative as well as right hand derivative at the point c will check. So here LF dash of c, this is the left hand derivative at the point c. Okay, that should be defined. Limit extends to c minus left hand derivative we are showing just for differentiation, minus we are taking. Okay, left hand derivative we are taking minus only, and f of x minus f of c by x minus c, and we are putting in this instead of x c minus h, where h is positive. H is greater than 0 means here the limit should becomes h is converges to 0. So here the limit extends to c minus place low. Instead of that, I am taking limit h tends to 0 plus. Okay, and instead of x here c minus h is there, right here c minus h minus f of c as it is by x minus c means c minus h minus c plus c should get cancelled. Here what is the remaining term? Minus h. Okay, this is the left hand derivative at the point c. Similarly, we'll see right hand derivative at the point c, that is r f dash of c. That should be is equal to, we can define limit extends to c plus right hand derivative we are showing with the plus only, and f of x minus f of c by x minus c same. Okay, and here we'll put instead of x c plus h in the left hand derivative c minus h. No, obviously here also h is positive, in this case also h is positive, but here in the RHS instead of x c plus h have to substitute. Okay, and limit h tends to 0 plus f of c plus h minus f of c by c plus h minus c plus c should get cancelled. No, remaining term is nothing but we should get h. So here both the limits are exist as well as equal. See here limit h tends to 0 plus f of c minus h minus f of c by minus h. Here f of c plus h minus f of c by h. Whatever both limits are equal, then only it should be satisfies the limit condition. Okay, one limit exist avalante enti, left hand limit as well as right hand limit should be exist, right? No, in the same as here left hand derivative as well as right hand derivative both are exist as well as both are equal at the point c belongs to open interval a comma b. So that's what my here it should be each point f dash of c we can take. That means since we know that f of c is nothing but what we have, capital M, that means least upper bound of the function f. Least upper bound means f of c minus h, this condition minus f of c is greater than less than or equal to 0. That means f of c minus h less than or equal to f of c we can take, as well as from the second condition also here f of c plus h minus f of c is also less than or equal to 0. That should be also we can write f of c minus f of c we can take on the right hand side, we should get f of c plus h less than or equal to f of c. Okay, we'll continue this. Yes, so now we are saying these two are less than or equal to 0. F of c minus h minus f of c is less than or equal to 0, and f of c plus h minus f of c is also less than or equal to 0. That means what, ma? Left hand derivative is greater than or equal to 0, right hand derivative is less than or equal to 0. That means two derivatives will be equal to each other. That should be equal to 0. So that means derivative of the constant value, that should be equal to 0. That is f dash of c equal to 0. Okay. So when similarly we have two real numbers we choose, c and d, right now. So here when m is small m equal to f of d, it is also different from f of a and f of b, same proof. Okay. So here we can prove that f dash of d is also 0 when d is nothing but element in a comma d. So this is the Rolle's theorem concept, ma. Very important theorem in third unit real analysis, ma. So okay, note this theorem, you should prepare well. Thank you.